Hello world, we're live, and today we're trying to solve, actually we're solving, we're looking at the solution of the problem that is in the category of dynamic programming. Um, that's the kind of solution we're using here. And let's take a look at the problem first. Yeah, so, and then go through the solutions. So, we should look at the problem first. And we have a grid m by n of numbers, and they're actually digits from 0 to 9. And we can change one value in one operation. We can actually change it to any non-negative number, not just those 10 digits. And you need to perform some operations such that, so such that in each cell, the value is equal to the cell below. Well, that base and different from the cell to the right. What that actually means is the whole column has to be the same value, like in this example. And different from the cell to the right means that it has to be different from its neighbors, essentially, left and right, if any of those exist. Return the minimum number of operations. And for this problem, we're using a dynamic programming solution. And I'm gonna share my notes. Notes to walk through the thought process. So let's have an example of if we have, for example, if we have in our input data 1, 0, 0, and 1, 0, 0, and we have 1, 1, 0. And I'm just thinking, because I think I should have gone through the more simple cases, those test cases that are in the examples. In the examples first, before we go to some bit more complicated examples. Well, so essentially, yeah, we'll look at the one example was 1, 1. Jeez, I'm just learning to use this pen, this electronic pen. That's why. So it's like that. That example is like that. And all of the columns have the same values. I mean, each column, in one column, there's only the same values, but the neighbors, all neighbors are different. So there is nothing to do in this example. We don't have to change anything. Now, the next example is, yeah, let me just point like this. The answer is 0. The next example is 1, 1, 1, 0, 0, 0. And here we could do either, yeah, we do need to change because we have neighbors are the same and columns are not the same. So not vertically is not equal. And we either can do like 0 here, 1 here, 0 here, right? So yeah, let's get it thicker. So it will be 1 here. It's either 0, changes that will change to 1, and that will change to 0. So that, or it will be the opposite. So that will be, yeah, so you see they're all the same now. 0s, 1s, and 0s. Or we could do, change everything to 1, 0, 1. Yeah, so, and both of them are 3. The answer is 3 for both. And the third test case is, for example, is the 1, 2, 3. And what's the answer? Well, in this case, you have to change to, yeah, you have to change to values because you need to make this, well, any of these. So yeah, you can make like these two or any, yeah. So the answer is 2. And okay, that's kind of the explanation. And but now let's look of the problem. Yeah, the problem statement. Let's look at a little bit more interesting example here. Yeah, and we have yeah, so we have these numbers. 1 here, 1 here, and 1 here, and 1 here. And I'm just practicing explaining the solution. let me go to the solution. It took me some time to figure it out. And I just don't go to the solution. I'm going to explain a little bit the logic behind it. Yeah, intuitively, I realized we need to like have the counts. It's kind of the important, yeah. And I think I should just jump to the solution here. Yeah. So the solution goes like this. We will count. Yeah, we'll use dynamic programming, and for each number digit, we have like here 0, we have num 1, and there could be 2. We could use a 2. That will be enough for now. So let's see at each column how many of those we have. So we go over the column, we count zeros, we have 2, and we count 1, we have 1, and 0, no 2s. Now we need to return the minimum number of changes we need to make. But the other way of saying it, we know that the maximum we could we could do is like change everything, like change all this to 2s, 3, I don't know, 4, whatever. Yeah, everything here. So that's a solution, and it will take m by n. Now, if the value is already there, that means we don't have to change. If we use it, actually, we don't have to change. So minus this value. Like if this number is there and we use it, so we don't have to change it. So minus that. So we're actually going to be looking for the maximum number of moves we don't have to make. Yeah, so we can avoid, so saving of the cost. And because that's what we count here. This is like 2. If we use zeros here, we already have 2 zeros, so we don't have to change. And that's how much we don't have to change if we use zeros. So for one column, this is essentially could be the data we need for the answer. We just find the maximum here, and we'll look at like, okay, this is the yeah, the maximum here is this 2. 2 is we'll use the 2 zeros that are already there, and so it will be like 3 minus 2, so we have to only do 1, and that's the answer. Okay. And for one column, and these are now that's I don't know, we could call it dp for like this. This array is the data that we need to solve this. And the best one is 2, but the thing is the trick here is not to try to find the answer, the final answer at each column. The trick is to try to have all the options and find the best and list them at every column. So when you go to the second column, and let me just make it a bit longer. Yeah, so we have some. We will look and we will see. Okay, we again have 2 zeros. We have 1. Yes, single 1. And we have a no 2s. And and the solution for these 2 columns, here's how we come to it. So if we look at each option here on this column 2, okay, this is the maximum, again, saving we can get. But at the same time, if we use this 0 here, yeah, if we turn, all these to zeros, we can't actually use, in that case, we can't actually use the 0 on the previous column. So what will be the savings? What is the best savings we can get if we use this, like we use this 2 here, so everything will become 0. We can't use 0 here, then we have other options to go here. Why don't we use the biggest saving that we can get, which will be to use 1s. And that is the biggest number, the biggest number that is not at this, that is not the same. Yeah, the biggest count, it's not actually the count, is the biggest solution, subsolution. Because the subsolutions will be going so that means we need to add 1, and if we have, like, we could save 2 here, we could save 1 on the first column, and both columns would be happy. They're gonna be vertically the same, horizontally different. Vertical, numbers will be the same in there, but horizontally they will be different. And while doing that, we will save 2 plus 1. So we will save 3. We will save actually 3. Or we can put 2 plus 1 for now. Now, in the second column, the same thing. Here we can use this existing saving, but we can't use it from the previous column. So we'll use the biggest one, which is 2, from the previous one. So plus 2 equals 3. And here it will be 0, plus the biggest previous 2, which is 2. And so these will be actually what we will gonna put in this column. 3, 3, 2. That's what we're actually going to put there. So it's gonna be, oops, it's gonna be 3, 3, 2. And now we're gonna go to the third. So these options are pretty much have the same value to us. Now this here we're gonna have the count. So we're gonna have 2 1s, 1 0, and 0 2s. And again, okay, what do we have for 1? It's yeah, we can use 1 0. If we do so, we'll be able to the best value of the other ones will be +3, 4. Yeah, here we also can use the other 3, the other value, so it will be 5. And here we have 0 plus 3, so it will be 3. So that's the, and by the way, so this was the solution for these 2, and this with this 4 is the solution for all 3 columns. Oops. And 4, 5, and 3, and the biggest saving we can get is 5 if we pick 1 here. So it will go like that. We'll pick 1 here. We'll pick well, that means we need to pick 0 here. And that means we'll need to pick 1, 1. So total, that's how many moves we need to make, but the total is 9 minus that 5. Why 9? Because we have 3 by 3 minus 5, so that's 4, and that's how many we have to do, like 1, 2, 3, 4 changes we have to make. So each column here, it stores not only the count in the respecting column, but it also stores the best solution from the previous columns. Yeah, from all the previous columns. And that's how it's solved. We can take a look at the code. If I stop sharing that. But essentially, that's how it goes. Yeah. So did I stop sharing? So I need to start. I need to reshare. Share. So I have some explanation there, but this is the code. We start with defining essentially the number of rows and the number of columns of the grid. what is the word? The dimensions of the grid. Then we define the variety of digits. The digits variety, we probably want to use that instead of just digits, which is 10. It's from, this is from 1 to 9, 0 to 9. And then we create a previous subsolution, which is going to be zeros initially to the length of 10. So this is going to be an array of the length 10 that has only zeros, 0 counts. These are actually counts. These are those sub-solutions that will have the counts plus the everything previously, but initially it's all zeros. And we need that empty sub-solution. It's like our dummy. Then we will go over all the columns. I think I should work on the names here. Yeah. So this is like rows. This is columns. This is digits variety. I think it was like that, yeah. This is variety. So columns will go over columns, rows will go over rows. And yeah, we'll go over columns. We create a current array for these sub-solutions. But the trick is, and one of the tricks here is when we don't really, if you remember that logic when we went over the row and over column after column, we always just referred to the previous column. We never needed the entire table. So we actually going to track only the current and the previous column here. So that's what that's all that we need. So we're going to go over that row now for a number of rows and read from the grid. And we're going to have the counts. So initially, this current is filled up with counts. Current counts. And that's all it gets for this row, for this column. Go over the rows. So it actually iterate the rows, so go over the column. So we're building that first column. And then, okay, we're going to go over that column again. Now we're going to go over the this sub-solution, which is now just has the counts currently. Current counts. It will look. So we will try to find the best in prev, other than for any other number. So we have our max initially to 0 and initialized, yeah, like that. And then we're going to go over the prev and over prev. And we're gonna check if it's not the same as the current digit. This is the digit. I, in this case, is digit. Yeah, so I is digit. J is previous index. This is also digit. Yeah. And if that I is not the same. So for all other, we say that, okay, max prev, we update the max. Okay, give me the bigger number. What's currently the max pref or what we had in the pref? So we find that maximum and we add it to our count for this digit, current count. So this is the solution that that satisfies everybody, and we save it. Yeah, like for this number, this is what will work for everyone so far. Then we copy current to pref, so the next current will be the pref from before. Yeah, the pref, I mean, will be pref will hold the pref, the previous current. And then at the end, we just go over the final row of pref, because pref will be at the end. Pref will hold the current. And find the maximum, and that's our answer. Yes, so current max undefined I. Yes, so we, instead of I, we use digit. And use digit instead of M, we use rows and calls. Yeah. So that's it. And it passes all tests, right? Yeah, it passes all tests. That's the solution. It uses, goes. The time complexity is, well, we have to go over the entire, all the numbers. So it's like n, if we count all the numbers n, and the space complexity is essentially 10, which is fixed. Well, that's the solution for this problem. Thank you for watching, and we'll see you in another video.